Let me introduce your speaker. Sorry about that, guys. Sam Newman is an independent consultant who loves solving problems with technology, focusing primarily on the areas of cloud, microservice architecture, and continuous delivery. Sam works with companies big and small all over the world. He's an experienced conference speaker and author of the O'Reilly books, Monolith to Microservices, Building Microservices, and the forthcoming Building Resilient Distributed Systems. The title of his talk, Definition of Insanity. Welcome, Sam Newman, everybody.
Thank you. Thank you. We're going to have a rail disruption announcement? No, we're good. All right, let's get going. Thanks so much for coming out. We're going to be learning a little bit about at least, well, maybe one person's definition of insanity and why it might not actually be insane at all. And as mentioned in the introduction, I am in the process of working on a book. More about that a bit later. But this content today is actually taken from the early parts of this book. This is a book that I'm writing at the moment because some idiots out there have been promoting the use of distributed systems in a context where they probably shouldn't be used. So kids, don't let your other friends do microservices. And if you do, you might need help. And that's kind of what I'm dealing with at the moment is like, well, now you've got this awful distributed mess. What do we do about it? In terms of stopping it from falling over, we're going to be talking today about timeouts, which is giving up, retries, which is trying again, and idempotency, which is what the heck do you do when you do try again, when you probably shouldn't have tried again in the first place. We're also going to be talking a little bit about this quite famous definition of insanity. The definition of insanity is doing things over and over again and expecting a different result. Turns out this is a statement flawed on many levels. But we can start off by talking about the context in which I'm speaking. When we're thinking about timeouts, retries, and idempotency, we're doing so in the context of a distributed system. If you're building a microservice architecture because you read a book and thought it was a good idea, you are building a distributed system. I would imagine that the vast majority of you are building a distributed system in one way, shape, or form. Some more, some are less distributed. But it is probably worth trying to define at least what I think a distributed system is. Okay, so my definition of a distributed system is very, very simple. It's a system which consists of two or more computers connected by a network. That's it. Starts to sound very simple, doesn't it? Two computers, one network, this is what we have. And the network is kind of one of the main important parts here because it turns out that this is where we get a lot of our problems from. The issue with my definition of a distributed system is it's quite dry, it's factual, it's objective, but it doesn't necessarily speak to what it's like to own and operate a distributed system. And that's where there's a different definition that I actually prefer to my own that comes from Leslie Lamport. A distributed system is one in which the failure of a computer you didn't even know existed could render your own computer unusable. And this actually speaks to the realities often of working with distributed systems. They fail in interesting ways, ways we may not have been able to predict. Now, of course, this could lead us to a discussion of things like Byzantine consensus protocols, whether you should do Raft or Paxos, you always do Raft. Whether or not cap theory can be defeated, it can't. Should you even use cap theory? Probably not. But really, it speaks to the fact that any distributed system can potentially be a little bit like a house of cards, that any one little small change you make may bring things down, crashing down around you. And it can feel overwhelming when you start looking into the literature around distributed systems. But I think in reality, we can peel back some of those layers of complexity and think, what is it about a distributed system that gives rise to all of this complexity that we have to deal with? And I think we can strip things down to 3 simple rules. Used to be 2, I've added a third, but I don't want to go beyond 3. So when thinking about a distributed system, what are the 3 main things that cause us pain and suffering? Firstly, you cannot beam information instantaneously between 2 points. This is not something that you can do in our known universe. I am aware there is a thing called quantum entanglement, but quantum entanglement only works for read states. And very importantly, it is not a networking protocol. So in a system, if I want to get information from here to here, it takes time. You are partially in control of how long that takes, but not wholly, never wholly in charge of how long that takes. It might appear to be instantaneous from the point of view of a user, but it's not, and it can vary. The second golden rule of distributed systems is that sometimes you can't reach the thing you want to talk to. Again, this is sometimes under your control. You might try and do things to make sure the thing you want to talk to is normally there, but you cannot guarantee that 100% of the time. This is reality. Doesn't mean you shouldn't try and make things more stable, but it does mean that you also have to be prepared for what happens when it isn't there. Or, even worse, it's like it's up, but you can't talk to it. We've all been in that situation where my computer is here and my printer is here. These are two computers, right? And they are both up, but they cannot talk to each other. We don't know why, right? This happens all the time in our own distributed systems. And the final challenge for distributed systems is that resource pools are not infinite. These issues are, I think, individually quite easy to understand and appreciate, but when taken in their entirety, gives rise to a whole swathe of complexity that we have to deal with. In this talk, I'm not going to be talking about all the really complicated stuff. I'm going to be talking about the foundational things that you, as a developer, need to get right. These are the foundational ideas that you need to do. Before you get to even have a conversation about Byzantine consensus protocols, you need to get good at timeouts, retries, and idempotency. It is deeply unsexy, but it is very practical, and it works. So we'll start off with timeouts. How boring is this? This is actually the heart of the basics, right? Timeouts. This is a threshold after which a request will be terminated if not completed. This is us giving up after a certain period of time. Timeouts are important. Why are timeouts important? Well, coming back to our rules, we cannot beam information instantaneously between 2 points. It could take a variable amount of time. Therefore, it makes sense to give up at a certain amount of time. And also, it makes sense to give up because you might be waiting for something that just isn't there. So if I'm trying to make a payment, as in this scenario here, I'm saying, I want to give you some money, but for whatever reason, I don't get a response. It probably makes sense for me to go, look, I've had enough. I'm not trying anymore. That's it. Very, very simple. Maybe, though, we should look at why we even do this. Why don't we just wait forever in these scenarios? Well, to break it down, there's a few reasons. When I establish a connection, when I'm trying to wait for something, even if I'm claiming I'm asynchronous because I'm using some kind of non-blocking I/O, I am using resources. So if I'm waiting for something, I'm busy waiting, right? I'm tying up computing resources. And that's kind of an issue, isn't it? Because the more we wait, the more resources are tied up, the faster it might be that we might achieve some level of saturation in our system, which in turn could imperil the health of our system as a whole. We also have other issues, of course. Often in an interconnected distributed system like a microservice architecture, the order service might decide to wait forever, but in reality, there are other things maybe waiting on the order service. Are they going to wait forever? And you can very quickly get into situations where a slow service with overly generous timeout, some way deep in a call stack, can end up contending resources all the way through the system, and I have more than once seen entire production outages caused by this sort of thing. So a lot of timeouts are about keeping our resource consumption within acceptable bounds. It's about ensuring that we recognize that our resource pools are not infinite and timing things out so we can free up computing resources. Getting them right can be a bit tricky. It can be difficult. If you time out too quickly, you may be giving up on something that might otherwise have worked, and that's just really annoying. You may have done 99% of the work, and just before you get to send that work back to whoever asked for it, the person who asked for it has given up. And you're like, but I was almost there, and they've gone. And that's galling because you've tied up time and resources not giving an answer. It could be compounded, of course, if they come back 30 seconds later and ask for it again. On the other hand, if you wait too long, you are going to increase resource contention, which can cause system instability. It can also make users unhappy as well. So what do we do? So how do we find good timeouts? Well, the first thing is to have an accurate understanding about what normal system behavior is. And so typically the first place I'm going to start with here is trying to look at things like the response time of the thing I'm talking to. So I normally want to see that in some kind of histogram. For those of you who haven't seen a histogram before, they are incredibly useful for these kinds of things. What a histogram is doing is showing you a number of occurrences. So as we go along the left here, from left to right, we are seeing requests that have increasing amounts of latency. So we can see we've had some successful requests here that took as long as 250 milliseconds. As we go up, we're talking about the number of times we saw a request with that degree of latency. So we can see here that 80 milliseconds is the kind of most common request time, right? Response time. What's useful here is we can start looking at shakes, we can start looking at distribution, and any observability tool worth its salt should be able to get this kind of view for you very, very easily. So we can see, for example, that these calls worked, but they took a very, very long time. This then starts allowing us to have conversations about where do we draw those timeouts. Do we wait for everything to finish, but recognizing that that might mean that we are waiting a lot longer than we might otherwise want to wait? So a common thing often in these scenarios is to say, well, if we wait just for these little outliers to actually respond, we're actually waiting around for a very long time for things that might also fail. And so is it better to give up on these outliers and to protect the health of the overall system? But we at least get to have that conversation if we have this picture. There's been lots of talks today and yesterday about having shared views, allowing us to have good conversations. This is a good example of that. But we also have to overlay user expectations. How long are the human beings in our system going to wait? We might look at our system performance and say, you know what, we could afford to wait 30 seconds for this operation to complete, and we wouldn't imperil the health of the system. Would that make sense if our users were going to get really bored and they were going to hit refresh anyway, or go off and do something else? Well, in such a situation, no, it makes no sense to wait longer than the end user would wait. The third thing, and this is quite important, is that make sure you can change the timeouts without changing code. So this is an example of, say, if I was using Resilience for J, which is like a little library for Java code. This gives me the ability to have like timeout and retry policies, and I can specify those in a simple text file like this. You definitely want this, otherwise things can go a bit awry. Fundamentally, though, a timeout is about prioritizing the health of the overall system over the health of an individual request. We're accepting the premise that we might give up on a request and therefore fail an individual request, but we're doing so in the hope that the whole system is more healthy. This is arguably the trolley problem, only maybe less visual. Another thing to note when thinking about timeouts and thinking about system behavior, in general, you do want your system behavior to be pretty consistent. If you have your normal behavior being quite varied in how long things take, it can be quite difficult for you to understand where to specify timeouts. If you've got a fairly kind of confined set of acceptable performance, it becomes much easier for you to assess when has something gone wrong. So in general, right, being consistently slow might actually be better than being inconsistently fast, because then it becomes much easier for you to assess how quickly things are going and therefore draw your lines accordingly. Like these two histograms have exactly the same number of calls. The second one, we're seeing a much tighter bound in how quickly things take. This one actually has some things being faster, but also some things being slower. This one, we're much tighter. So you'll find it much easier to draw lines and work out timeout boundaries. One other thing to mention here before we move on, these outliers here, these are often called high percentile latencies. these tail latencies. We could do a whole talk on them. I've kind of implied you should just give up on them. That's not strictly always true, because we do need to remember these are typically human beings, and you've probably annoyed them. So that's probably a talk in and out of itself. We've given up. We've given up, so now do we want to try again? Does trying again make sense? The definition of insanity would imply it doesn't make sense. However, we also know that that is true. But why is that true? Why is this statement, at least in the context of our distributed systems, manifestly wrong? Well, because sometimes you think you can't reach the thing you want to talk to, and often that is ephemeral. One of my favorite system outages was once caused by rabbits. I mentioned earlier that you're not entirely in control of these situations. You're not entirely in charge of something not being there when you want it to be there. In my situation, I was working in an engineering company. We had ducting that ran between the various buildings. We had our networks running through that ducting, and these things called rabbits, which you may be aware of in the natural world, thought, that looks like a ready-made burrow, and they moved it. And if there's one thing that rabbits like more than anything else, it's like electrical insulation. They love it. And they ate the network, right? Now, could we have foreseen this? Probably not. How do you control for rabbits? I don't want to go into pest control, but having pest control in your risk register, it's an interesting thing. But often we have all kinds of maybe less fun or less interesting types of failure scenarios. Consider a very simple situation where I've sent a request to a service which has multiple instances. My initial request may have been routed to a service instance which is suffering from some kind of instability. Maybe it was already on its knees. Maybe it started load shedding. Maybe it's just being wiped out by the Kubernetes out-of-memory killer. It's a very evocative thing. I'm going to kill you because you've got no memory. And in such a situation, though, we know there are other instances available that could help us out, and therefore trying again manifestly would make sense, because there's a very good chance that a subsequent attempt would find us reaching a node which can help us out. We recognize that lots of things that go wrong in a distributed system can very much be ephemeral. So retrying makes sense. So if at first you don't succeed, it may be worth trying again. How many retries should you do? 0, 1, 1,000,000. Probably somewhere between those numbers, right? If you're thinking about how many retries you should do, there's a whole lot of balancing forces that come into play. Because you've also got to take into account how long will people wait. Retry too often, you're causing resource contention. You're waiting, you're tying things up for longer periods of time, and the users themselves may give up. Not retrying enough may see you fail things that could otherwise have worked. So again, it's that little bit of a dance. So remembering this resource is not infinite, you have to be very, very careful. Retry too often, you might overload a server. Your initial request may have failed because that instance was suffering from some issues. It was kind of close, it's resource saturation. Your request pushed it over the limit, and that's why it didn't respond. And you deal with that by coming back again and going, no, seriously, what though? Can I have it now? And you keep coming back again and again and again. So in these types of situations, the retrying over and over again may not make sense. So this is why we have a maximum number of retries. And this would normally be set on some people might have defaults across the system, but in many cases, it makes sense to vary that in particular cases. And obviously, in these situations, in a situation where you're worried about the server being sort of at peak saturation, a sensible defense here is to practice some load shedding. So basically allowing a service to, at a certain point, throw work away when it's over limit, right? By setting a maximum number of retries, you're partly providing defense for the server on the client side. You're also partly dealing with user expectation. A server instance itself, though, should know what an acceptable level of request handling is and get rid of work above that threshold anyway. I find people very rarely practice load shedding. You should. As with timeouts, ensure your retries can be changed without code changes or redeploys. So to give you a practical example of why this might be an issue, back in 2017, Square had a massive outage. This was caused by their multi-pass authentication system that went down. When it came back up, it was trying to get a lot of data from Redis. Redis was overwhelmed, and the multi-pass just kept pounding Redis, saying, no, I want it now, I want it now. So it was a hard-coded 500 retries in the multipass code with no delays between that whatsoever. So basically, this was a self-inflicted denial of service attack. It just kept going again and again and again. And of course, they saw it not start, so people were restarting the multipass nodes, and then it just started all over again. So it was a bit of hard-coded Go code. They had to go and fix it. Right? If those things had been externalized, they would be easy enough to fix with a simple text file change or a configuration store change. They've done a lovely write-up, by the way. So this is one thing I love about our industry is some companies are excellent at saying, we did this thing, and this bad stuff happened. Why don't you learn from our mistakes as well? So I urge you, if you've ever had a fun outage in your company or a non-fun outage in your company, if you're able to share it, all of us benefit. Do we need delays between retries? Well, yes, normally we do. And that's because we recognize that often the circumstances which caused the initial failure might persist if we immediately attempt a retry. So having some kind of delay between retries is absolutely something that makes sense. We want to kind of, rather than having a repeated hit going on, want to space out those retries a little bit to ensure that we are reducing the chance that the services we're talking to become overwhelmed. We do have to be careful, though, even with those gaps, about making those gaps regular. Because what can happen is that you can start getting the situation where you get waves of retries all arriving at once. So this scenario here, we've got some kind of calls coming in, and a bunch of them have sort of pushed us over our kind of normal happy saturation level of resources. And so a portion of those calls above that red line are going to start timing out because we've reached the capacity levels of our system. So some of those calls time out, right? They then have a fixed delay, and then those calls that timed out come back again a fixed period of time later. And they arrive all together, and they ensure that we're definitely going to get pushed over that limit once again. So now we've got more calls that are over that limit, a portion of which might work, a portion of which don't, and so they end up coming back again, and we can end up in this peak where these peaks get bigger and bigger, and they can get really, really big to the point where it can be catastrophic. So what we want to do is we want to space out these retries. There's two kind of main ways we can do this. The first thing to do is to use some jitter. So jitter is a term in networking that basically refers to some variation in latency. And this just comes from the physical nature of our networks. But what we're going to be doing is adding some artificial jitter into our retry policy. So this could just be a random amount of time that will be added. Now, if you're using something like Poly in .NET, or you're using Resilience4J in Java, they have built-in jitter things that you can push and you use. Those libraries are great in that they give you tools that you can put together to make these calls more resilient. You kind of need to know how to configure them. So they'll have things like retry policies. They'll have timeout policies. They'll do jitter for you. So being aware of why you're using jitter is what I'm getting at here. So this is going to help space things out. So this is the same number of calls, but now we are just spacing them out a little bit more so we don't get those horrible troughs. Another thing that's often done to cite, so if we look at these kind of in comparison, this is the same number of calls. This is sort of an artificial scenario, but you get the idea. The same number of calls, but now we've just applied an amount of jitter. And what we're doing is we're kind of taking down those peaks and actually starting to fill in some of those troughs a little bit, which is also kind of just a more efficient use of our computers as well. Another way to space out retries is often cited is to some people say use an exponential backoff. Yes-ish. The thing about exponential backoff, so if I'm going to wait 100 milliseconds before my first retry, then 200, then 400. The problem with fully exponential backoffs is they're exponential. And what we know with exponential is they get big fast. And so if you're suddenly going from a very small to very big delays between your retries, think about your overall timeout of that operation. So it's quite common, in fact, that people will use kind of semi-exponentials. They might do, they might not add 100%, they might add 50% to those delays. Again, things like Poly and Resilience4J give you a very easy mechanisms for changing these things. So if you are going to go full exponential, you probably do want to have some safeguards in for how long that overall operation took. This then leads us on to kind of a more tricky aspect of all of this. Is it even safe to retry? So in a scenario like this, I'm placing an order. I want to give Sam £100. I'm very passionate that Sam, after his performance today and his lovely shirt, gets £100. We can buy more fancy shirts. So if you want to contribute money towards me, my PayPal link will be at the end of the presentation. But I want to give Sam £100, right? But we don't get a response. So what could have happened? I've tried to give you £100 and I didn't get a response. What could have happened? The first possibility is that something has happened to that initial request. That request was not picked up and it was not processed. It might be that the request never reached the payment service in the way that we expect. And remember, of course, we might get a connection established, what we think is a service, but it could actually be a gateway. It could even be that we think the request got to the service itself, but the service crashed while processing it. But fundamentally, in this scenario, we didn't get a response because the request wasn't processed. And that is one scenario. And from the point of view of the client, that's quite possible. The other possibility, of course, when the client does not get a response, is that the request was received, but the response got lost. So again, this could be that the payment service did the processing, and just before it sent the response, the process crashed. We have things like transactional outboxes to help resolve that issue, but it's still a possibility. Could also be, of course, that the response came back and got misrouted. There was a network issue at the time the response went back. The network connection got broken. There's a lot of scenarios in which they could happen. But from the point of view of the client, I sent the request, I didn't get the response. I do not know which of these two possibilities has actually occurred. And I cannot know with perfect accuracy. And so the issue is, when I send that pay Sam £100 request, if I don't get a response, but it turned out that the payment was actually made, if I go and make that request again, I could end up in a situation where Sam is paid twice. Now, speaking personally, I'm very happy with this scenario. Just for future reference, happy to get paid multiple times for not doing extra work. But this, of course, is probably not suitable in our systems. We want to be able to retry, because there are lots of situations where short-term issues cause something to fail, and retrying would cause something to work. Being able to retry makes it easier for our systems to be more robust. But for us to be able to retry, we need to make sure that those retries are safe. And this leads us on to our third concept for the day, and that is idempotency. So this is all about making retries safe, and this primarily applies in the context of write operations. But an idempotent operation is an operation that we can do repeated times without changing the result. So as we've shown so far, this particular operation here is not idempotent. We reattempt the same operation, and we get a different result. Because the first operation, Sam got £100. The second operation, Sam has got £200. So we've reattempted, the operation is not idempotent in this particular example. So how do we make operations idempotent? There's two real key ways of doing it. One is nice and easy and a right pain to retrofit into existing systems, and that's request IDs. But planning for this up front makes your life very easy. The other option is server-side fingerprinting, which is something which can be useful in legacy applications where you can't change client-server protocols. In rare occasions, you will use these things together, but that's kind of a bit niche. Let's start with the easy one, request IDs. With a request ID, what we're going to do is create a unique ID to identify a specific request. Note that this is not the same thing as, say, a trace ID, because a trace ID would be used across a set of calls. This would be for an individual call. This also wouldn't be the same thing as a span ID, because, again, in telemetry, retries would show up as separate spans. So this has to be a separate thing. The idea being here that when I go and say, pay Sam £100, I have some unique ID. Here it's 456. So if the payment service carries out that payment against that request ID, it knows that completed. We send the response back. The response gets lost. The payment is reattempted, with this same information, and we can identify that that request has already been processed. And something as simple as storing this in a database table is absolutely fine, most of the time. Right? That was processed, stick in a database table, next request comes in, do we already have that request ID? If we do, give them the same result, move on with our lives. There's some nuances here a little bit. If you've got any questions about this, do remember to ask questions via Slido, and if we have time, I'll answer them at the end. Now, one of the problems is that request IDs require a change in the client-server protocol. This becomes effectively a required field from the client. What if that cannot easily be changed? I work with a lot of teams who have not seen failed requests often enough to realize the importance of idempotency. And they've dealt with these issues as isolated bugs, and then suddenly realize this exists, and they realize we've already got a system, we've got lots of client-server protocols, but we don't have request IDs. So what can we do about that? Well, one option is to consider server-side fingerprinting. And this is a lot more fiddly and complicated, but might be a good approach if you are facing that challenge of retrofitting these ideas into older software. What we're going to do is we're going to generate a fingerprint of the server side on the server side. And we're going to use that to identify duplicate requests. So in this scenario here, I'm sending the payment. We can imagine this is our HTTP request. And so what you would do is effectively the header would contain metadata. And this obviously would apply equally well to a message-based system. So you ignore the metadata. You take the body of what you're being sent. And in this example, we're going to generate an MD5 hash. Obviously, there are other schemes if you're worried about MD5 hash collision. Again, that is also a topic we could have a whole talk on. So in this example here, we've taken those fields and we generated an MD5 hash. We would then store that locally on the payment side. If we get a request that comes in, we could take a look at the body, do these hashes match. So what are the issues with server-side fingerprinting? Oh, there are a bunch. One of the first ones is often there are things in the bodies that might actually vary between retries. So in this particular example, for whatever reason, we've got a timestamp of when the request was attempted is actually in the body itself. And so between these two requests, in that retry event, that timestamp has incremented. So if we're just taking the fingerprint of the body, the fingerprint would have changed. It will appear as though this is a brand new request, even though semantically it isn't. So how will we solve for this problem? Well, what we could do is mask. And again, this is probably what you're going to be doing. So you're probably going to end up saying, OK, if I've got a body, parts of which can change, on the server side now, you're going to have to exclude some fields from your fingerprinting. And this is fiddly and potentially error-prone. Of course, the right answer, and you're all thinking it, Sam, why is it in the body? It should actually be in the header. And you're absolutely correct. However, if you could make changes like that, it implies you could change the client-server protocol. And if you can change the client-server protocol, just use a request ID. So this is one of the challenges we can have with server-side fingerprinting is like there's things in the body that shouldn't be in the body. But by definition, it's a legacy system that it's hard to change. You may not have much of a choice there. Another issue with server-side fingerprinting is time. You've paid Sam £100, but you really want to support my work. And you think, I want to pay Sam £100 on a regular basis. So you pay Sam £100, we generate a hash. Time passes, a week comes by, and you think, I haven't sent Sam any money recently. Let me send Sam another £100. Okay. I'm trying to do that NLP manipulation thing I've heard so much about. I don't think I'm doing it right. Anyway, a week passes, and let's say, send Sam another £100, but the hashes will be identical. But semantically, this second operation is a new operation. But it appears to be exactly the same as the previous operation. So what can we do in this scenario? Well, we could then apply some kind of period of validity for our fingerprints. How long that period of validity is going to be down to the context in which you're operating. It could be a minute. It could be 100 seconds. It could be 10 seconds. It could be a week. It depends in the domain you're operating in. This, though, could be a real problem if you're operating in a space where doing what looks like the same thing over and over again, quite close together, is actually part of how people will use your system. Think about an API that allows you to spin up a bunch of containers or a bunch of VMs. I might have a for loop around an API, and I want to spin up 5 of the same VM. Each of those requests will look identical. They're all going to be done very, very closely together, and I want there to be 5 of them. If that is the way people are using your API, server-side fingerprinting isn't going to work, which is exactly why all the cloud vendors have request IDs. Now, actually, the cloud vendors, well, certainly on AWS, they actually do request IDs and they do server-side fingerprinting. You don't have to deal with that because that's something the SDKs you'll use for, say, AWS hide behind. But the reason they do this is because if you send a retry, but you vary the body, so you send a retry with the same request ID but vary the body, that is actually considered to be an error, and you'll be told that this is an error. And this is partly an education tool. This could be useful inside an organization where you're trying to implement request IDs. If you see people keeping the request ID but varying the body, and that's not supposed to be allowed, you could actually use that as a way of going back and erroring, and this can be like an internal education piece. On that notion of what we send back, when we send back a response that we've already sent, but for some reason the client didn't get, what should we be sending back? Should I just go, I've had that before? Well, actually, no. What you do is you deliver the same response as you delivered the first time, or attempted to deliver the first time. So if the first attempt worked, you just send back it worked, with exactly the same information. If the first attempt failed, because you're being asked to do something that you couldn't do, so pay Sam £100, Sam hasn't got £100. He's only got £50 in his account. You don't see that response, you retry it, you send it back. No, that request you sent failed because Sam didn't have enough money in his account. You just send back the same response. So in this case here, it happened to work. So when I try again, I just send back exactly the same response. Now, you can have metadata in there to indicate, look, I told you it worked. This is the 5th time I've told you it works. Please take the hint. You can still put metadata in to show that this has been sent multiple times. But you don't want a special case for this. Whatever happened the first time, you just send it the second and subsequent times. So, in summary, if you can change the client-server protocol, request IDs are by far and away the easiest way to make an operation idempotent. So in any kind of request-response-based interaction, whether it's over a message broker, using some kind of HTTP-based protocol, just generate a unique ID, put that into a formal part of your specification for your client-server protocol. It's a required field. Do it from the beginning. Your life becomes very, very easy. Because then you can make any write operation idempotent. For reads, you don't have to worry as much about this necessarily. If you already found yourself in a situation thinking, oh dear, we've already done this, and retrofitting it is going to be a pain, and you want your clients to be able to retry, then put server-side fingerprinting in. If you don't do either, then you're in a world where your clients cannot safely retry. And then you might say, don't retry. And then you might be in a world where one failure can never be reattempted. Sometimes systems are OK like that. You're going to have to work out if that's the case for yourself. But in general, allowing clients to retry operations is the way to go. So it turns out doing the same thing over and over again might actually be very sensible, but only if we do it safely. Speaking of doing the same thing over and over again, I'm sure many of you, hands up if you've seen this quote before, right? This famous quote by Einstein, only he never said that, ever. This is one of the many things that Einstein never said. Right? But we keep saying he did, didn't we? So we keep saying over and over again, Einstein said, the definition of insanity is. So I'm actually felt glad that the statement about the definition of insanity is clearly massively flawed, and it turns out Einstein didn't say it. That's actually kind of worked out well for us. So, your 3 rules of distributed systems. When all around you is noise and chaos and you can't understand what's going on, that is an emergent property of the fact that you are working in a system where you cannot beam information instantaneously between 2 points. Sometimes you can't reach the thing you want to talk to, and resources are not infinite. You can control for some of these. You can throw more computing hardware at the problem to increase your resource pools. You can have multiple copies of things to deal with failover scenarios. You can get nice high-speed fiber interconnects to try and speed up latency, but there will be things that happen outside of your control that might affect all of those things, and you need to be prepared for it when it occurs. When you should give up, work out what your timeout should be. Every call should have some kind of timeout, be it a request sent over a message broker where you're waiting for a response, or via something more direct like a point-to-point HTTP connection. If at first you don't succeed, retrying absolutely makes sense, as long as you can limit how often it happens and make sure all of these things are configurable outside of your code. And it is vital that if you want to make retrying safe, you're going to need to make those operations idempotent. So look at request IDs. With that out of the way, you can download the slides here at this QR code. If you know more information about my book, that will take you to that location as well. You can find information about my book. You can sign up for a newsletter there where I give you updates about what's happening. The first 6 or 7 chapters are available in early access on O'Reilly.com, including, believe it or not, I've got way more to talk about just about timeouts. I've got like 7,000 words just on timeouts. It was the most fun I've had in like 10 years of writing was writing that chapter. You can go read chapters on timeouts, retries, idempotency, rate limiting, load shedding, thundering herds, all right now. But thank you so much for your time.